Let's now look at k-nearest neighbors. So k-nearest neighbors consists in having a reference data set. So similarly to an histogram or kernel density estimation, we have some data set at n, and we want to, for example, make density estimation by looking at the samples that are close. So more specifically, looking at the k closest samples from our data sets to the x point that we care. So this is more or less equivalent to make an estimation based on local estimation. So it is a local data density estimation based on the k closest data. And that is basically consisting of saying, okay, we have k data, and we are dividing this by the dk. dk is in fact, the distance from the kth neighbor to the x data in our data set. So we say, what is the distance from my current x to the k nearest neighbor? So for example, if we use k equal to 3, so we are looking at the 3 closest neighbors, we can say, okay, we have our x here that we care, and we have several points here. What we are looking at is to say what are the three nearest neighbors of our point here, this one, that one, and that one. So that's fine. So what is the farthest closest, the farthest point in our k closest data? It is that one here. And so we are looking at the distance between our x and that data that give us the dk here that we care. And so this is a way to have, I would say, some kind of adaptive window. So we are looking at an adaptive window, and we are using that h, we are adapting that h value according to this distance, to the kth neighbor. This is a non-continuous estimator, and so as such, it is similar to a naive histogram estimator, but this time using an adaptive h value. So this k nearest neighbor approach is basically defined by 3 parameters. We first have to define the number of neighbors that we are using. So with a k that is low, or eventually even a k equal to 1, where we are looking at the nearest neighbor directly, the space is divided by really small bins. And so every bin is centered on one of the sample that we have in our data set. So really, if in our reference data set, we don't have samples in some region, the bins will be big there, but will be really small in the denser area of the domain. With a higher k, everything is much more smoother. So we have inference of many samples around the current value, and these samples can be relatively far from the current samples, current x values, the x value that we care. So as such, it gives us a smoother estimation, but possibly less precise. And if we are looking at the distance measurement, we can define the neighborhood as function d. So the function d is measuring the relationship between the data. And we have a reference data set. So basically, number of neighbors, the distance measure, that can be Euclidean distance or something else, and the reference data set, which are the data that we are using for our KNN evaluation. And this reference data set is giving us the density of the distribution in the data space according to our samples. The point is, we often want to use data that are representative. So sometimes we may need to look at filtering the data. We will see some methods for that later on in the presentation this week. So we were looking at first at kernel density estimation from KNN. I would say that I show that as an introduction, but I don't want to insist on that because this is not super good. I would say it's even relatively poor way to make density estimation. So k-nearest neighbor density estimation is not interesting, is not performing well at all. While K and N for classification is really interesting. This is, I would say, one of the first well-performing method for classification that has been proposed. It is dating back from the 60s. It is easy to implement. It was usable on computers of the 60s. And it works as a good baseline. Of course, our modern methods are much better in general at performing, but if we want to get a good baseline to compare ourselves with, KNN classification is a good baseline for that. Usually we should try to do better on this, even though the performance of KNN is good. So for making k-nearest neighbors classification, we need to get a reference data set. We call this a reference, but it is basically the training data set that we were using before for estimating, for example, the parameters for parametric classification. So we have our data set, which is made of n samples, which are the data set and the label corresponding to the data itself. And so we want to classify an unknown data by computing its k closest neighbors in X using distance measure. So we have some kind of Euclidean distance. And so, for example, or something else, can be something different, but we are looking at some distance measure to compute the k closest points in our data set from our unknown data or unknown point X, which we want to process. And as such, we are assigning the X to the most frequent label among those k nearest neighbors. So we are looking at the k nearest neighbors, we are looking at their labels, and we are getting a vote. So we are making the nearest neighbors to vote to their label class, to their class, associated to it themselves, somehow, to the label of the data of the k closest neighbors. And we are assigning X to the class that has the most votes. So it's very simple, very direct method for classification. It makes sense, you know. We are looking at the k nearest neighbors, and we are looking at the majority of the class which is the most frequent, and we are assigning our data to that class that is the most frequent. With k equal to 1, we are basically dividing the input space according to what we call a Voronoi diagram based on the X data set. Voronoi diagram is basically to define regions of influence. So we have a point here, and we have in this Voronoi cell all the area where that point is the nearest point among all points in our data set. So an example here, we have two classes. We have the blue squares, we have the red triangles, and we have the green circle we want to classify. So if we are looking, for example, at the 3 nearest neighbors, so we are looking at the 3 samples among all data instances here, among the blue squares and red triangles, the 3 nearest neighbors are what we have inside this circle here. So the full line black circle. So we can see here that we have 2 instances that are red triangles, 1 instance that is the blue square. And as such, we will assign our sample to the class of red triangles because we have 2 of them close to our sample. However, if we are looking at the 5 nearest neighbors, we will look at a neighborhood that is corresponding more or less to the circle with dashed lines. So that big circle is giving us more or less the area we are looking for 5 neighbors with that center on that point on the green circle. And there, this is different. We have 3/5 that are blue squares and 2/5 that are red triangles. And then the classification is different. We are assigning our point to the blue squares. If we are looking at a Voronoi diagram, which is presenting how we are splitting the space according to the samples, we can see here an example of that. So basically each black dots are samples. We have one point center there, and all the color kind of polygon around it correspond to its Voronoi cell, where this black dot is the nearest point among all the points we have here. The frontiers between the cells are basically the points where we want to I would say make decisions. So 1 minute. So we see that here, for example, this is the point where we are on the frontier between this and that point. So if we are making like nearest neighbor classification, it means that a sample here will be assigned to the class from that point, and a sample there will be assigned to a class of that point. So this is a way to split the space according to the different samples. Of course, we don't have one class per sample here. This is an example of how we are splitting the space according to the samples, but not more than that. Now we also have another case where we have the three classes. We have the red, the blue, and the green. And as such, when we are doing 1 and n, k equal to 1, so nearest neighbor classification, we have as a result this thing. So we have, I would say, a bunch of regions, green, blue, and red, that are corresponding to the decisions made from nearest neighbor classification. We can do kind of fancy stuff. We can see here, there is a lot of small patches according to a different class, likewise here. So possibly these are, I would say, great examples of overfitting, because we are memorizing our samples and we are making classification based on the one instance each time, like that thing here, that thing there. So this is not good. I would say in terms of generalization, performance should be relatively poor. When we are looking at the borders for 5 nearest neighbor classification, we have something quite different. So we have something where the samples are classified differently. So we have this region of blue, red, and green, and we have these things here, but it is much less present than in other places.